In the first part of this video lecture, we saw some applications of the convergence theorems of the previous video lecture. So we saw that when a sequence of random variables converges to another variable at almost surely on little omega, and these random variables are bounded by a finite number, then their expectations also converge. And we showed a proof of this corollary. Then two exercises that we gave some hints but did not quite show the proof is the inverse of the monotone convergence theorem. It's now when you converge from above rather than from below. And here we need to assume that f1 is integrable, and in that case we also have the convergence of the integrals. And we also saw this exercise that if this the expectation of the absolute value of a sequence of random variables is summable, then this random series of numbers converges almost surely, converges and is finite. And the expectation of this, the random result of this infinite sum of random numbers is the same as the sum over n of the expectations of each number alone. Now we see two more exercises for you. One is clearly one that now really uses the monotone convergence theorem because it's a sequence of non-negative, non-decreasing measurable functions. So measurable function is already implicit in the statement of the exercise. We don't work with non-measurable functions. And if the expectation of each of these f's in the sequence is less than a certain constant m for some finite number m, then this limiting function f that we get in the limit, well, almost surely, or for almost every omega, it will be for almost every omega, because this is a measure space, not a probability space, not necessarily. This function f of omega will be finite. Now we see here something that looks very much like Fatou's lemma, except that everything is reversed. The lim sup is here where before it was a lim inf. The lim sup is here where before there was a lim inf. And the inequality here is different from the inequality we would see in Fatou's lemma. So this is a nice exercise to expand on what we saw already and use what we have in the right way to do the cancellations in the correct way, making sure we didn't leave any loose cables or loose ends in the argument, and do some magic trick playing with these f's and g's, maybe trying to copy what was done, trying to mimic what was done in the proof of the dominated convergence theorem. So this the statement of these two exercises and this short video lecture, or this small part, this short part of this video lecture. And now here is we keeping our promise that we can indeed differentiate inside a moment generating function. So how was it? We have a random variable x. We can always define this expectation because the exponential of real numbers is always non-negative, and non-negative random variables, they always have an expectation. Maybe it's infinite. Well, we call this expectation m of t, and now we think of it as a function of t, and this function is called the moment generating function. And well, for all this to work, we need to assume that there exists some number, some positive number, such that this moment generating function is finite when the parameter is, when the argument is small than this number. Okay, so there's a tiny interval, at least a tiny interval containing 0, where this moment generating function is finite. And under this assumption, well, since the moment generating function is finite, we can try to compute derivatives of this function. And here's the kth derivative of this function, evaluated at t equals 0, and the proposition says this is the kth moment of the random variable x. This is what the proposition says, and well, you know what is the wrong proof of this proposition, it would be simply m prime of t. It is, well, the derivative with respect to t of this expectation of e to the tx, and we want to enter this derivative here, and that's what this entire video lecture and the previous one are about, commuting expectations with limits. If we could commute this, then of course this would become the expectation of the derivative with respect to t of this number, and this, we know how to differentiate an exponential. This would become the expectation of x times e to the tx. And now when we plug in t equals 0, what we get is just the expectation of x. And we can do the same for the first derivative, second derivative, and so on and so forth. Because this is a known proof of the proposition, but it's actually the core of the proof. The core of the proof is to justify this step here. So let me stop here. We take a break. You go read or you go do something else, and the next video will be a rather tough one. We'll do the entire proof of this proposition.